A deep hum resonates across the cosmos, the sound of two dead stars crashing together. This is the story of a binary neutron star merger, one of the universe's most violent and creative acts. By the end of this journey, you will understand how these cataclysmic events forge the very elements that make up our world and even our own bodies. We will uncover what happens in the final, frantic moments before impact and explore the mysterious afterglow that rewrites our cosmic history. What does it feel like to witness the birth of gold in the heart of a dying star? That deep hum originates from objects of almost impossible density. These are neutron stars, the collapsed cores of massive stars that have exhausted their fuel and exploded in supernova. Picture a star many times more massive than our own sun, crushing itself down under its own immense gravity. All that remains is a sphere no wider than a city, yet containing more mass than our entire sun. A single sugar cube-sized piece of this material would weigh as much as every human on Earth combined. This staggering density is possible because the star's incredible gravity smashes atoms together, fusing electrons and protons into a solid sea of neutrons. The entire object becomes a single, gigantic atomic nucleus, a perfect sphere of the most exotic matter in the universe, but the strangeness does not stop there. Neutron stars also possess magnetic fields so powerful they could strip the information from every credit card on our planet from a distance halfway to the moon. And their gravity is so intense that the fabric of space-time itself warps around them. It is this combination of unimaginable density, ferocious magnetism, and extreme gravity that makes these stellar corpses so potent. When two of them are locked in a final, deadly dance, the stage is set for a cosmic event that truly forges the world we know. Such a pair does not simply appear. They are born from chaos, the twin remnants of two massive stars that once lived and died together. Picture a stellar nursery, a vast cloud of gas and dust where new stars ignite. Sometimes massive stars are born as siblings, a binary pair orbiting one another. For millions of years, they burn bright and stable. But a star's life is a constant battle between the outward push of nuclear fusion and the inward crush of its own gravity. When the fuel in their cores finally runs out, that balance shatters. Each star, in its turn, explodes in a supernova of unimaginable power, an event so violent it can outshine an entire galaxy. Yet, against all odds, this catastrophic explosion can be so perfectly symmetrical that it does not blow the binary pair apart. The bond of gravity survives the stellar death. What remains after the fire fades are two impossibly dense cores, two neutron stars, still locked in their ancient orbital embrace. Their dance is now a slow, silent spiral across the galaxy, a waltz measured in millennia. They are drawn ever closer by an invisible force, their orbital energy slowly being stolen away. This slow, silent waltz cannot last forever. The same gravity that binds these stellar corpses together also seals their fate, not with a sudden pull, but with a persistent, invisible drain on their motion. They are losing energy with every orbit, radiating it away in the form of ripples in the very fabric of the cosmos. These are gravitational waves, a phenomenon predicted by Albert Einstein over a century ago. Think of space-time not as an empty stage, but as a vast, flexible trampoline. When massive objects like neutron stars orbit one another, they do not simply move through this fabric, they distort it. Their immense mass churns the space-time around them, sending out waves of distortion that travel outward at the speed of light. Each wave carries away a tiny, almost imperceptible amount of the system's orbital energy. This loss is the engine of their doom. Over hundreds of millions of years, this steady drain of energy relentlessly pulls the two stars closer together. Their orbital dance accelerates from a slow, stately waltz into a frantic, ever-quickening spiral. The final orbits are measured not in millennia, but in milliseconds, a dizzying blur of motion as the two city-sized spheres of pure nuclear matter hurtle toward their inevitable merger. This cosmic death spiral, driven by the emission of gravitational waves, is the universe's ultimate countdown clock, ticking down to a single, spectacular moment of creation and destruction. This death spiral accelerates into a final, frenzied rush. The two neutron stars, now only a few hundred miles apart, are moving at nearly half the speed of light. Their orbital dance becomes a blur, completing entire revolutions in mere milliseconds. At these extreme speeds and proximity, the incredible gravitational forces at play begin to tear the stars apart from the outside in. Imagine the ocean's tide, but amplified by a factor of billions. The side of each star facing its partner is pulled far more powerfully than the side facing away, stretching the entire city-sized sphere into a teardrop shape. This is a tidal force of cosmic proportions, so violent it begins to rip streams of ultra-dense neutron-rich material from the star's surfaces. These long, spiraling tendrils of stellar matter are flung out into the space between them, creating a seething, hot whirlpool of exotic particles. As this happens, the stars emit one last, deafening scream across the universe. The frequency and amplitude of their gravitational waves skyrocket, producing a final, intense chirp that shakes the very fabric of space-time. Simultaneously, this violent interaction unleashes a brilliant flash across the entire electromagnetic spectrum, from radio waves to gamma rays. This is the birth of a multi-messenger event. For the first time, we are not just seeing or hearing the cosmos, we are doing both at once. The gravitational waves carry the story of the masses and the orbital dynamics, while the light tells us about the hot, ejected material and the nuclear physics at work. Together, they provide a complete picture of the cataclysm, a symphony of information from a single, transformative source. The moment of impact is a flash of pure creation. The two spheres of degenerate matter do not so much collide as they merge into a single, violently unstable object. For a few precious milliseconds, a new celestial body is born from the wreckage, a hypermassive neutron star containing the combined mass of its parents. Think of this object as a single, city-sized droplet of the most extreme material in existence, spinning so fast it completes multiple rotations every second. It is temporarily supported not by nuclear fusion, but by the sheer, frantic motion of its own rotation and the complex nuclear forces battling against an unimaginable gravitational crush. This is a state of matter that cannot exist anywhere else in the universe, a fleeting, turbulent fireball of pure potential. But such an object is inherently unstable, a dam about to burst under the weight of its own existence. If the combined mass is too great, this brief resistance fails catastrophically. The immense gravity overwhelms every other force in a sudden, final victory. In less time than it takes to blink, the entire structure gives way. The boundary of the object, known as the event horizon, silently forms at its center and rapidly expands outward, swallowing the newborn star whole. Where a moment before there was a maelstrom of incandescent matter, there is now only absolute nothingness, a black hole. The energy released in this instantaneous collapse is staggering, far greater than the sun will emit over its entire 10 billion-year lifetime. This energy does not emerge as light, but is imprinted onto the very fabric of space-time, a final, powerful tremor in the gravitational wave signal that marks the birth of a new darkness at the heart of the cosmic storm. Yet this collapse is not the end of the story. It is the trigger for a final, spectacular act of cosmic alchemy. The violent merger and the subsequent formation of a black hole do not capture all the material. A small but crucial fraction of that ultra-dense, neutron-rich matter is flung away at incredible speeds, forming vast, hot clouds around the newborn singularity. Within these expanding clouds, trillions upon trillions of free neutrons are now available, and they are captured by atomic seed nuclei at a staggering rate. This is the rapid neutron capture process, or the R process, the universe's primary forge for the heaviest elements. Think of a snowball rolling down an impossibly steep hill, gathering more and more snow with every instant until it becomes a colossal boulder. In the same way, atomic nuclei within these clouds snatch up dozens of neutrons in the blink of an eye, building elements far heavier than iron, elements that ordinary stars could never create. This furious bout of neutron capture creates wildly unstable, overweight nuclei. They immediately seek stability through radioactive decay, a process that unleashes a phenomenal amount of energy. This energy powers a brilliant, short-lived fireball known as a kilonova. The event gets its name from its incredible brightness, which can be thousands of times greater than a typical nova. But unlike a supernova that can shine for months, a kilonova is a transient flash. It blooms into a distinctive, rapidly fading glow, primarily in the optical and infrared parts of the spectrum, as the expanding cloud of newly forged heavy elements cools and becomes transparent. That specific infrared signature is the telltale fingerprint of cosmic gold, platinum, and even radioactive elements like uranium being created and scattered into the void. So the next time you hold a piece of jewelry, consider its origin. The gold in that ring was not born in the heart of a star, but in the furious, radioactive aftermath of two dead stars colliding, a fleeting kilonova that seeded the galaxy with the very ingredients for planets, for life, and for us. That faint cosmic chirp, the final gravitational scream of two dying stars, finally reached Earth on August 17, 2017. After a century of theoretical prediction, the twin LIGO observatories in the United States and the Virgo detector in Italy felt the unmistakable ripple in spacetime. The signal, officially named GW170817, was not the brief thud of black holes merging, but something entirely new. It was a song that started low and quiet, a hum that grew steadily in both pitch and volume for about 100 seconds. This was the sound of the neutron star's final, accelerating death spiral, a direct audio recording of their last 30,000 orbits before collision. The signal culminated in a crescendo, that final, intense chirp marking the moment of merger itself. Then, something even more remarkable happened. Just 1.7 seconds after the gravitational waves peaked, NASA's Fermi Space Telescope detected a powerful, short gamma ray burst from the exact same patch of sky. This was the confirmation everyone had hoped for. For decades, astronomers had theorized that merging neutron stars were the engine behind these brief, mysterious blasts of high-energy light. In that single moment, with one gravitational wave signal and one flash of gamma rays, a major cosmic mystery was solved. The data from the waves themselves told a detailed story. By analyzing the subtle differences in when the ripple arrived at each of the three widely separated detectors, scientists could triangulate its origin to a region of the southern sky. The characteristics of the signal revealed the masses of the objects involved, confirming they were indeed neutron stars, not black holes. This event was not just a detection, it was the dawn of a new era in astronomy, one where we could both hear and see the universe's most violent dramas unfold. That single, coordinated alert sent a shockwave through the global astronomy community. Within hours, the race was on. From mountaintop observatories in Chile to radio dishes in New Mexico, and from orbiting telescopes like Hubble to the Swift satellite, every available eye in the scientific world turned toward that one patch of sky in the constellation Hydra. This was not a planned observation, it was a cosmic scavenger hunt triggered by a whisper from spacetime itself. The goal was to find the visible afterglow of the collision, the electromagnetic counterpart to the gravitational wave chirp. For the first time, we were not just listening to the universe, we were hunting for the source of the sound with every tool at our disposal, and they found it. Less than 11 hours after the initial detection, optical telescopes at the Los Campanas Observatory in Chile spotted a brand new pinprick of light in a galaxy known as NGC 4993. It was a faint, bluish glow that had not been there the night before. This was the Kilonovae, the radioactive glow of heavy elements freshly forged in the stellar cataclysm. The identification was the starting pistol for the most intensive observational campaign in history. For weeks and months, astronomers tracked this single point of light as it evolved. They watched its color shift from brilliant blue to deep red as the expanding cloud of material cooled and the heavier elements within it became dominant. They studied its spectrum, reading the chemical fingerprints of cosmic gold, platinum, and lanthanides being blown into interstellar space. They monitored it with X-ray and radio telescopes, which later detected the lingering afterglow from a jet of material that had been launched during the merger at nearly the speed of light. This was multi-messenger astronomy in its full, breathtaking glory. The gravitational waves told us the masses and the dynamics of the dance. The light across all wavelengths revealed the physical consequences, the chemistry, and the aftermath. It was like hearing the score of a symphony and then suddenly being able to see the orchestra, the conductor, and the instruments all playing in perfect, coordinated harmony. This single event confirmed decades of theory in one fell swoop, transforming our understanding of the cosmos from a silent movie into a full sensory experience. Detecting these whispers from the cosmos requires an instrument of almost impossible sensitivity. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is not a single telescope but a pair of identical facilities separated by 1,900 miles, one in Washington state and the other in Louisiana. Each one is shaped like a giant letter L, with two arms stretching 2.5 miles into the distance. This entire structure is built to do one thing: measure a change in distance smaller than 1/10,000th the width of a proton. To understand how that is even possible, picture the core of each detector. Down the center of each multi-mile-long arm runs an ultra-stable laser beam, housed in the largest vacuum system on Earth to eliminate any interference from air. This single laser beam is split in two, with one half sent down each arm to bounce off a mirror suspended at the far end. In a perfectly calm universe, the two beams would travel the exact same distance and return to cancel each other out in perfect darkness. But when a gravitational wave passes through the Earth, it does something extraordinary. It subtly stretches the fabric of space in one direction while squeezing it in the perpendicular direction. For a fraction of a second, one arm of the detector becomes minutely longer while the other becomes minutely shorter. This tiny difference, a shift in length far smaller than a single atom, means the two laser beams no longer return in perfect sync. They fall out of step by less than a billionth of a meter, and this creates an infinitesimally small flicker of light where there was once only darkness. That flicker is the signal. It is the direct evidence that space-time itself has been stretched and squeezed by a cosmic event that may have occurred billions of light years away. This entire monumental apparatus, with its seismic isolation systems, its suspended mirrors, and its pristine vacuum, exists to capture that one nearly imperceptible glimmer of light. To confirm the signal is real and not some local tremor, both LIGO detectors, along with their partners Virgo in Italy and KAGR in Japan, must see the same ripple in space-time within the tiny window of time it takes light to travel between them. This global network acts as a single ear, listening for the faintest hum of the universe's most violent events and pinpointing their location in the vast cosmic ocean. That faint infrared glow from a kilonova is more than just a cosmic light show. It is the visible signature of the universe building itself atom by atom. For decades, scientists believed that the heaviest elements were forged primarily in the cores of supernova explosions. But the detection of that single merger in 2017 fundamentally rewrote that story. We now understand that the violent crucible of colliding neutron stars is the universe's primary foundry for creating about half of all elements heavier than iron. This process, known as the rapid neutron capture process or the R process, is a frantic race against time that can only occur in the most extreme environments imaginable. Picture a single atomic seed, perhaps an iron nucleus, suddenly caught in a blizzard of free neutrons. In the calm interior of an ordinary star, a nucleus might capture one neutron and then have time to stabilize before capturing another. But here, in the expanding debris of a kilonova, the density of neutrons is so astronomically high that the nucleus is bombarded. It does not have time to breathe. It captures dozens of neutrons in a fraction of a second, building up into an impossibly heavy, wildly unstable version of itself. This overweight nucleus is so saturated with neutrons that it immediately seeks balance. It undergoes a rapid series of radioactive decays, transforming some of those neutrons into protons. This act of decay changes the very identity of the element, climbing the periodic table to create entirely new, stable heavyweights like gold, platinum, and neodymium. The energy released by this furious decay is what powers the kilonova's brilliant, transient glow. Without these cosmic collisions scattering their freshly minted elements across the galaxy, the periodic table would be a much emptier place. Our planet would lack the rare earth metals essential for modern technology. There would be no platinum for catalytic converters, no radioactive uranium to heat the Earth's core, and most poetically, no gold for a wedding ring. Every heavy atom in our bodies and our world carries the echo of a cataclysm that occurred billions of years ago, a direct inheritance from the explosive deaths of distant dancing stars. That newborn object born from the collision exists on a knife's edge. Its ultimate fate, whether it becomes a permanent black hole or briefly shines as something even stranger, hinges on a single critical factor: its total mass. If the combined mass of the two neutron stars is greater than a specific threshold, roughly 2.2 to 2.5 times the mass of our Sun, then the battle is over in an instant. The newborn hypermassive neutron star's own gravity is simply too immense. No known force in the universe can support it, and it collapses into a black hole within a fraction of a second. There is no time for anything else to happen. The object is born and then it is gone. But what if the total mass is just below that critical limit? This is where the story takes a truly bizarre turn. In this scenario, the merger can create a stable, or at least a temporarily stable, neutron star. And not just any neutron star, but one spinning at an almost incomprehensible rate. This object is a magnetar, a neutron star on steroids. It possesses the density of a neutron star, but its magnetic field is 1,000 times more powerful, and it is rotating hundreds of times every single second. This frantic spin provides an extra outward force, like a cosmic centrifuge, helping it to resist the relentless inward pull of its own gravity for a little while longer. For anywhere from a few milliseconds to perhaps several hours, this magnetar becomes the most powerful object in its local universe. Its incredible spin and magnetic field act like a colossal engine, driving intense outflows of energy and particles into the surrounding debris. This can dramatically change the appearance of the kilonova, making it brighter and longer lasting. But this reprieve is only temporary. The magnetar is bleeding energy constantly, emitting powerful gravitational waves and electromagnetic radiation. As it loses energy, its spin slows down. The very force that was propping it up begins to fade, and the balance shifts. Eventually, the crushing weight of gravity wins its long war. The magnetar, too, succumbs and collapses, leaving behind a black hole as its final legacy. So the afterglow we see in the sky holds a hidden message, a clue about the final, fleeting moments of that central object and the precise cosmic scales that decided its fate. The brilliant flash of gamma rays that arrived just moments after the gravitational wave signal was no coincidence. It was the final, focused scream of light from the merger, a beacon of pure energy so intense it briefly outshone every other source of gamma rays in the entire observable universe. This is a short gamma ray burst, a cosmic flashbulb that lasts for less than 2 seconds. Yet in that fleeting instant, it unleashes more energy than our Sun will emit across its entire 10 billion-year lifetime. The source of this phenomenal power is not the collision itself, but its most dramatic aftermath. As the two neutron stars merge and the resulting object collapses into a black hole, a chaotic whirlpool of superheated matter forms around it, an accretion disk spinning at nearly the speed of light. In the midst of this chaos, the newborn black hole and its magnetic fields act like a colossal cosmic engine. They can funnel a tiny fraction of this infalling material into two narrow, powerful jets that erupt from the poles of the system. These jets are not simple streams of gas. They are focused beams of plasma and radiation accelerated to over 99.9% the speed of light, making them what scientists call relativistic jets. The physics within these jets is so extreme that it generates the concentrated blast of gamma rays we observe. But here is the catch: this lighthouse beam is incredibly narrow. For us to witness it as a short gamma ray burst, one of those jets must be pointed almost directly at Earth. If the jet is aimed elsewhere in the cosmos, we might detect the gravitational waves and the kilonova's glow, but we would miss the main event, the brilliant flash of high-energy light. This precise alignment is incredibly rare, which is why detecting a gamma ray burst in conjunction with gravitational waves, as we did in 2017, was such a monumental event. It confirmed that these fleeting, mysterious flashes are the universe's way of signaling the violent birth of a new black hole from the debris of a stellar collision. While the brilliant flash of a kilonova fades within days, the story is far from over. Radio telescopes around the world begin a patient, years-long vigil, tuning into the whispers of the expanding debris. These observations capture a different kind of light, one that reveals the long-term aftermath of the cataclysm. The initial fireball of the kilonova expands outward, but it is not alone. Often, the merger launches those narrow, relativistic jets at nearly the speed of light. For weeks or months after the collision, these jets plow through the thin gas of the interstellar medium, the sparse material floating between the stars. This interaction is not a silent journey. As the jet rams into this cosmic fog, it creates a powerful shockwave like a sonic boom in space. This shockwave accelerates charged particles to incredible speeds, causing them to radiate brightly at radio wavelength. This radio afterglow can take weeks to reach its peak and then fade slowly over months or even years. By monitoring this slow-motion fade, astronomers can perform a kind of cosmic autopsy. They can measure the total energy of the jet, the density of the surrounding space, and the geometry of the explosion. It is like listening to the echo of a thunderclap long after the lightning has vanished, using that echo to map the shape of the valley it traveled through. This long-term radio data provides the final, crucial chapter in the story of a merger, detailing how its energy is ultimately dissipated and how it seeds the galaxy with newly forged elements for generations to come. That brief, brilliant flash of a kilonova is the most productive foundry we have ever observed. In a single event, these collisions forge an almost incomprehensible quantity of heavy elements. Based on the data from that first detected merger, astronomers estimate it produced a cloud of gold with a mass several times that of our entire planet. Picture all the gold ever mined by humanity throughout our entire history, a total estimated at around 200,000 metric tons. Now imagine a single cosmic event creating more than the weight of 10 Earths in pure gold alone. If we were to put a price tag on that one event, the sheer volume of precious metals would dwarf our entire global economy into irrelevance. the numbers become meaningless, stretching into octillions of dollars, a figure so large it has no practical anchor in our world. This is not a resource to be exploited, but a testament to the universe's vast and indifferent productive power. The gold in your jewelry is priceless not because of its scarcity on Earth, but because of its impossible journey from a cataclysm that scattered these atoms across light years of empty space, eventually allowing them to coalesce into a planet where life could form and learn to value their glitter. The very idea of mining a kilonova remnant is a concept for a civilization far in the future, one that has mastered interstellar travel and harnessed energies we can barely dream of. They would not be chasing asteroids of solid metal, but rather capturing and processing an entire, expanding cloud of radioactive dust and vapor, separating elements atom by atom. For us today, the true value of this cosmic gold is not economic but scientific. It is the key to understanding our own origin, a glittering clue that we are, quite literally, made from the ashes of the most violent and beautiful events in the cosmos. Catching one of these cosmic symphonies requires a perfect alignment of luck, technology, and human ingenuity. The first and most daunting challenge is sheer distance and rarity. While neutron star mergers happen frequently across the universe, they are scattered across billions of galaxies. For their gravitational wave chirp to be strong enough for our detectors to hear, the event must be relatively close in cosmic terms, within a few 100 million light-years. Even within that vast volume, a detectable merger might only occur once every few months or years. It is like trying to hear a specific conversation in a crowded stadium from a mile away, while only being able to listen for a few seconds at a time. Then comes the race against the clock. Once the automated systems at LIGO and Virgo identify a candidate signal, an alert is sent to astronomers worldwide within minutes. This triggers a frantic scramble, as observatories must interrupt their scheduled observations and swivel toward the predicted region of sky, an area that can contain millions of stars. They are chasing a firefly that is fading fast, a kilonova that will dim significantly in just a day or two. Every minute of clear weather, every second of telescope time becomes precious. The final hurdle is the data itself. The initial gravitational wave signal is often buried in a sea of terrestrial noise, from rumbling trucks to minor earthquakes. Distinguishing a true cosmic ripple from these false alarms is a monumental task of statistical analysis and supercomputer-powered filtering. Each detection is a testament to a global network of scientists and engineers working in perfect, rapid-fire harmony, all to capture a single, fleeting whisper from the dark. This cosmic data is a goldmine for scientists, but unlocking its secrets requires recreating the entire event inside a supercomputer. These are not simple animations, they are full-blown digital universes governed by the most complex laws of physics we know. Each simulation must account for Einstein's theory of general relativity, which dictates how the stars warp spacetime, the nuclear physics that defines how their ultra-dense matter behaves, and the magnetohydrodynamics of their incredibly powerful magnetic fields. All these forces interact in a chaotic dance that is impossible to solve with pen and paper. So researchers build virtual neutron stars, set them on a collision course, and let the equations play out over millions of CPU hours. The result is a movie of the merger, predicting everything from the frequency of the final gravitational wave chirp to the amount of gold forged in the explosion. Then comes the crucial part, the comparison. The real-world data from events like GW170817 acts as the ultimate judge. Does the simulated gravitational wave signal match the one we actually recorded? Does the predicted brightness and color of the kilonova align with what the telescope saw? When the simulation and the observation disagree, it is not a failure, it is a breakthrough. It means our understanding of the physics inside a neutron star is incomplete. Perhaps the material is stiffer or squishier than we thought. Maybe the role of magnetic fields is even more dramatic. Each discrepancy forces theorists back to their digital drawing boards to tweak the fundamental rules of their models. This iterative process, this constant conversation between digital prediction and cosmic observation, is how we are slowly deciphering the true nature of matter under the most extreme conditions the universe can muster. Our current ability to hear these cosmic whispers is just the beginning. The next generation of observatories, already in advanced planning stages, will transform our faint murmurs into a roaring chorus. The Einstein Telescope, a future underground gravitational wave observatory in Europe, promises a sensitivity 100 times greater than our current detectors. By being buried deep beneath the surface and using a triangular configuration of 3 separate arms, it will silence the seismic grumblings of the Earth itself, allowing it to listen to mergers from the very edge of the observable universe. This means we could detect not just 1 or 2 events per year, but potentially several every single day, building a true census of how often these cosmic forges ignite. At the same time, the space-based LIS mission will open an entirely new window, a low-frequency one. While ground-based detectors hear the final, frantic milliseconds of a merger, LIS has 3 spacecraft, flying in a perfect triangle millions of miles apart, will sense the gentle hum of neutron stars spiraling together for years, even decades before they finally collide. It will give us a cosmic early warning system, telling astronomers exactly where and when to point their telescopes for the final, spectacular flash. In space, new observatories like the James Webb Space Telescope and its successors will peer with even greater infrared precision into the hearts of these kilonovae, reading their chemical fingerprints with a clarity we can only dream of today. Together, this network will not just find more collisions, it will allow us to dissect them from their earliest whispers to their final, element-scattering size, revealing the precise recipes that build our material world from stellar chaos. These cosmic collisions are far more than just spectacular light shows, they are laboratories of ultimate extremes. When 2 neutron stars merge, they create conditions of density, gravity, and magnetism that are impossible to replicate in any experiment on Earth. This allows us to conduct fundamental tests of physics by simply observing the aftermath. We can probe the very nature of matter itself. The core of a neutron star is a realm of pure speculation, a substance whose true state remains one of the greatest unsolved puzzles in physics. Is it a perfect fluid of free-flowing neutrons, or a solid crust of exotic nuclear posture, or perhaps a superfluid of strange quarks? Each possibility would cause the star to behave differently when it is stretched and torn apart by its partner. The precise way the stars deform during their final orbits, imprinted onto the gravitational wave signal, gives us a direct measurement of this stiffness. A squishier star deforms more easily, altering the gravitational wave chirp in a subtle but detectable way. By matching the observed waves to our simulations, we can effectively rule out entire classes of theoretical models, homing in on the actual recipe for matter at its absolute densest. This is not a gentle probe, it is a cosmic hammer, smashing matter together to see what truly holds it apart from nothingness. The merger also puts Einstein's theory of general relativity through its most grueling test. In the final frenzied moments, gravity is not a gentle background force, it is a dynamic, screaming entity. Our models for predicting the gravitational waves rely entirely on the equations of general relativity. When the signal we receive matches the prediction with astonishing precision, as it did in 2017, it is a triumphant confirmation that Einstein's vision holds true even in this violent arena. But what if a future detection shows a tiny, unexplained deviation? That would be even more exciting, a crack in the foundation pointing toward new physics, perhaps a hint of quantum gravity or hidden dimensions. Every merger is a direct experiment run for us by the universe, testing the laws that govern reality itself under pressures that defy comprehension. The silent dance of two dead stars is often invisible to our telescopes, but sometimes one partner reveals itself with a rhythmic pulse. This is the signature of a pulsar, a rapidly spinning neutron star that sweeps a beam of radiation across space like a cosmic lighthouse. When astronomers find one of these ticking clocks orbiting another dense object, they have discovered a natural laboratory of unparalleled precision. The clockwork regularity of a pulsar's spin allows for measurements of exquisite accuracy. As it moves through its orbit, the timing of its pulses is subtly affected by the Doppler effect, the same phenomenon that changes the pitch of a siren as it passes you. By tracking these minuscule variations in the pulse arrival times over years and even decades, scientists can map the entire orbit of the system. They can measure the masses of both objects with incredible precision, and they can watch for tiny, cumulative changes in the orbital period. This is where the ghostly presence of gravitational waves becomes tangible. Even in a system that will not merge for billions of years, the steady loss of orbital energy to gravitational radiation causes the orbit to shrink by an imperceptible amount. The pulsar's unwavering tick acts as a stopwatch for this decay. A predicted shift of a few millionths of a second over many years is exactly what was observed in the first binary pulsar discovered in 1974, providing the first indirect but compelling evidence for gravitational waves years before their direct detection. Beyond confirming Einstein's prediction, these binary pulsar systems are the census takers for future mergers. By discovering and timing them, we build a statistical picture of how many such pairs exist in the galaxy, how close they are, and what their masses are. This tells us the population of potential merger progenitors, allowing us to predict how often we should expect to hear the final, fatal chirp of a collision from across the cosmos. Each ticking binary is a premonition, a slow-motion preview of a future cataclysm that will one day forge the elements of new worlds. This faint cosmic chirp carries a secret within its waveform, a built-in measurement of its own distance that requires no assumptions. Gravitational waves are what scientists call standard sirens. Think of a siren on a passing emergency vehicle. You hear its pitch drop as it moves away from you, a classic Doppler effect. But there is another clue in that sound, its volume. A siren very close to you is deafeningly loud, while the same siren miles away is just a faint whisper. Your brain instinctively uses the loudness to judge the distance. Gravitational waves work in exactly the same way. The amplitude of the waves we detect, their loudness, tells us directly how far away the source is. A louder signal means a closer event, a quieter one means it is more distant. This is profoundly different from how astronomers usually measure cosmic distances. Traditionally, they rely on a complex chain of methods known as the cosmic distance ladder. Each rung of this ladder depends on the one below it. You might use parallax to measure the distance to nearby stars, then use those stars to calibrate the brightness of certain variable stars in farther galaxies, and so on. Any small error or uncertainty in a lower rung is magnified as you climb higher, leading to a growing fuzziness in our measurements of the universe's expansion. A standard siren bypasses this entire ladder. The gravitational wave signal gives us the distance to the merger directly and absolutely, just from the loudness of the space-time ripple. Then, by finding the host galaxy with optical telescopes, we learn how much the light from that galaxy has been stretched or redshifted by the expansion of the universe. By combining these two pieces of information, the direct distance from the waves and the redshift from the light, we get a completely independent and clean measurement of the Hubble constant, the rate at which the universe is expanding. Every neutron star merger we detect is a new, precise rung on this new cosmic ladder, helping us resolve one of the most significant tensions in modern cosmology. This grand cosmic search is not reserved for a few elite scientists in ivory towers. The hunt for these space-time whispers and spinning stellar lighthouses is a project that now welcomes the entire world. Your very own home computer could be the instrument that discovers the next pulsar or helps confirm a gravitational wave signal. Projects like Einstein at home harness the collective power of thousands of personal computers, creating a virtual supercomputer dedicated to sifting through mountains of astrophysical data. The principle is beautifully simple. While you sleep or during moments your computer sits idle, it downloads a small chunk of data from a radio telescope or a gravitational wave observatory. Your machine then quietly processes this data in the background, running complex algorithms that search for the faint, rhythmic signature of a pulsar or the subtle statistical fingerprints of a wave. Once the analysis is complete, your computer sends the results back to the scientists and automatically fetches a new piece of the cosmic puzzle. You are not just donating power, you are performing a vital part of the analysis itself. This is not a screensaver, it is a direct pipeline to the frontier of discovery. Everyday people, from students to retirees, have had their names listed as co-authors on scientific papers for identifying previously unknown celestial objects. They are true participants in the process, turning their everyday technology into a telescope capable of seeing into the heart of our galaxy. This collective effort embodies a profound shift, transforming science from a distant observation into a shared, human experience where anyone with curiosity and an internet connection can contribute to rewriting our map of the universe. This entire epic begins not with a collision, but with a birth inside a stellar nursery, a vast cloud of gas and dust. Two massive stars ignite within this cosmic cradle, bound together by gravity from their very first moments. For millions of years, they burn through their hydrogen fuel in a stable, brilliant partnership, their nuclear furnaces holding gravity at bay. But this balance is temporary. The more massive a star, the faster it consumes its fuel. Eventually, the core of one star exhausts its hydrogen and begins fusing heavier elements, a process that leads to a layered structure like a cosmic onion. This continues until iron ash accumulates at its heart. Iron fusion consumes energy instead of releasing it, and in that instant, the star's internal support vanishes. Its core collapses in less than a second, triggering a cataclysmic rebound that blows the star's outer layers into space in a supernova explosion, an event so bright it can outshine an entire galaxy. Miraculously, the bond with its companion star can survive this stellar suicide. The explosion is so symmetrical that it kicks the newborn neutron star core, this city-sized remnant of incredible density, but does not necessarily destroy the binary system. The same drama then unfolds for the second star. It too lives, burns, and dies in a supernova, and if the binary survives this second violent birth, two neutron stars are left orbiting one another in a silent, dark dance. Their waltz is measured in eons, a slow pirouette across the galaxy, but it is a dance with a doomed cadence, emitting gravitational waves with every orbit. They lose energy, drawing inexorably closer. For hundreds of millions of years, this spiral continues, almost imperceptibly slow at first. The final chapter, however, is breathtakingly fast. The last 1,000 orbits take only a few minutes. The last few orbits are a millisecond blur. The two dead stars, now just miles apart, rip each other apart with tidal forces, flinging streams of neutron-rich matter into a hot, swirling maelstrom. And then, in a final flash of light and a crescendo of gravitational waves, they merge. The timeline of a universe from stellar birth to stellar death culminates in a single, transformative instant that seeds the void with the stuff of worlds. That faint whisper from colliding stars forces us to confront a profound and humbling truth. We exist within a cosmos of breathtaking violence, a universe that creates the conditions for life through acts of catastrophic destruction. The very atoms that form your hands, your heart, the device you are using right now, were forged in these stellar explosions. Your body contains iron from the core of a long-dead star, oxygen blown out by a supernova, and gold that was minted in the furious aftermath of a neutron star collision. We are not merely inhabitants of this universe, we are its literal remembrances, walking archives of ancient cosmic fire. This connection raises a fundamental question about our place in the grand scheme. Does this violent origin diminish our significance, or does it deepen it? We are the universe becomes self-aware, a way for the cosmos to look back upon itself and comprehend its own astonishing history. The calcium in your bones, the phosphorus in your DNA, the iodine that regulates your metabolism, all were delivered across light years by these indifferent cataclysmic events. Our technology, too, is built upon this cosmic inheritance. The rare earth elements in smartphones and electric vehicles, the platinum in fuel cells, the uranium that can power cities or weapons, all trace their lineage back to the R process in a kilonova. Our entire modern civilization is built upon the scattered ashes of dead stars. This leads to a poignant reflection on the long-term fate of matter itself. The elements forged in these mergers will one day be incorporated into new stars, new planets, and perhaps on some distant world, new life. The gold in a future alien civilization's artifacts might be built from the very same atoms that once resided in a ring on Earth. Our individual lives are fleeting, but the matter that constitutes us is eternal, cycling through the galaxy in an endless dance of death and rebirth. We are temporary custodians of ancient stardust, gifted with a brief, brilliant moment of consciousness to appreciate the sublime and violent beauty of our own origins. The universe's grandest forges are not found on any planet, but in the violent, beautiful death of two stars. From their silent, eons-long waltz to the final, space-time-shaking collision, a binary neutron star merger is the ultimate crucible of creation. It is the event that forges the gold in our jewelry, the platinum in our technology, and the radioactive elements that heat the very core of our world. These collisions are more than just cosmic fireworks. They are fundamental laboratories, testing the laws of physics under conditions we can never recreate. They reveal the nature of matter itself and measure the expansion of our entire universe. Every flash of light and every ripple in space-time tells a part of this incredible story. So the next time you find yourself under a clear night sky, look up. Let your eyes wander to the darkness between the stars. In that vast silence, know that the cosmic drama is ongoing. Distant suns are being born, living, and dying in spectacular explosions that will one day seed new worlds with the promise of life. The same elements that make you who you are still being scattered across the galaxy, in a cycle of destruction and creation as old as time. You are a part of this epic, a living witness to a universe that is both violently chaotic and stunningly creative. All you have to do is look up and